Hello, and welcome to Calculus Lesson 133. Today we're going to do Euler's method, and it should be quite a bit of fun. So Euler's method is a way that you can approximate a function using only its derivative. So just like slope fields, where sometimes we can't find the original function, you can still use that to approximate the function using its derivative. So here's the idea. You have some function, and let's say it does that, okay? Now, all you have is a starting point, which is a point on the function, and you know where you want to get the, you know where you want to get a new value. So let's say this is a point 1, and you want to get the value of the function at 1.5. Okay, well, if you can't solve this differential equation, if you can't take the derivative and bring it back to the original function, you can use Euler's method. The idea is this. You're going to find the tangent line, and that's going to give you a new point at, let's say, 1.1. Now, that new point is no longer on your curve, but it's an approximation. It's on the tangent line. Then, we're going to use the derivative at 1.1 to approximate at 1.2. So that's going to get me there. Then we're going to use the derivative at 1.2 to approximate at 1.3, 1.4, and then 1.5. It's probably not going to be exact, but it'll at least get you close to the actual value. Now, if that sounds like a lot of work, don't worry about it, because it's really not. Here's your formula that you use. I would highly recommend plugging this into your calculator so that you can just plug and chug. So your new y, or let's call it y1, is y0 plus the derivative at the point xy. Remember, you have the x-coordinate, you have the y-coordinate, so you can do that, times delta x. So what we're doing is we're taking the slope times the distance we're traveling on each step and adding that to our original y value. If you do that, you can get to the approximation of the y value that you want. Now, with that said, the more subintervals, the smaller steps you take, the better approximation you're going to get. The book will give you how many steps to do. So don't worry about choosing that. They will give that for you, to you. So, mixing my words today. So let's try this one. Use Euler's method. I know it's spelled Euler, but it's Euler. Okay, it's a German thing. Use Euler's method with 5 iterations. So we know we're going to do 5 of these to approximate the value of y when x equals 1.5. So this is what we want. We want to know when x equals 1.5, what does y equal? Now, they give us an initial condition, which is 1, 1, and the differential equation dy by dx equals 2x. Now, obviously, we could integrate this. We can find the actual solution, but the problem is asking you to use Euler's method, so use Euler's method. You're going to use this equation, y1 equals y0 plus dy by dx, which is 2x, times delta x. So this begs the question, what is my delta x? Well, if I am going from 1 to 1.5, I'm going to do 1.5 minus 1 over the number of subintervals. So it's like b minus a over n, like we did for infinite summation so many lessons, like 100 lessons ago. The value you want minus your starting value divided by the number of iterations. So each of our iterations is going to have a delta x of 0.1, just like in the example over here. Okay, so y naught is 1 plus 2, x is 1 at this case, delta x is 0.1. So this gets me y1, which is 1.2. Then I'm going to find y2. y2 is y1 plus 2x delta x, which is, well, my y1 was 1.2. This is like Newton's method, is one of those iterative ones. Plus 2x is now 1.1, right? Before it was 1, but now I'm using the new x. Delta x is still 0.1. So if I were to write x numbers on this, this would be x0, this would be x1. Okay? Now, when we compute that, we get 1.42. Then we do it again. y3 equals y2 plus 2x2 delta x equals y2 was 1.42 plus 2x2. Remember, I was going from 1.1. Now I should be up 1.2. I'm just adding delta x each time. Times delta x. What do I get? 1.66. And we continue until we get to y5. And that's going to equal 2.2. So that is our approximation of the value of this function at x equals 1.5. We get 2.2. Now, just a quick trick, because the computer science in me is like, man, it's just killing me. Okay, how can you plug this into your calculator where you just press enter a bunch of times and then it works? Okay, that is a great question. So really what you want to do is you're going to take the answer from before. Okay, you probably should have some x variable that you increment each time by 0.1. But you could do answer plus 2x, right? Just plugging in your derivative times your delta x, which is always 0.1, and just keep pressing enter a bunch of times. You do that, and that won't work. Nah, sorry. There's no easy way to do it on the calculator. I would encourage you to write a program that does this so that it increments, it finds your delta x for you, it increments this, your x value, by delta x each time, and you can easily do that. So that, my friends, is problem set 133.